All right. Yeah, we're glad to have Shubhangi all the way from Toronto. She used to be here a lot more when she was closer by. Anyway, she'll tell us about some new arithmetic law.
Thanks, Avi. It's a pleasure to be here. I will tell you all about set-multilinear branching program lower bounds. Please feel free to stop, interrupt, ask questions, etc. I can go at a pace. Okay, so I'll explain the title, why we care about branching programs, why we care about set-multilinear branching programs. So I'll start off with giving some background and context about why we care about this question. I'll state some new results and try to say a few words about the proof. So arithmetic circuit, this is probably an object familiar to most of you. You're computing a polynomial as output, and you take as input variables and constants from a field, and you add and multiply them, and you get a polynomial as output. And you can talk about the depth of the circuit, which is the number of layers from output to input to output. The size of the circuit is the number of gates. The degree of the circuit is the max degree of any monomial appearing at any gate. Arithmetic formulas are like circuits, but when the underlying graph is a tree, so you cannot reuse computation. And it's known that if you have a circuit of depth delta, or the number of product layers from output to input is at most delta, then with a blow up, with delta and the exponent blow up in the size, you can convert a circuit to a formula. That's one object. So there was circuits, it was formulas. This is third object, which we will be primarily interested in this talk, which is arithmetic branching programs or algebraic branching programs, which are the following. So you're computing, again, polynomials, but the way the computation proceeds is the following. You have an input start node and an end node. And then you have these intermediate nodes, which are the layers of the branching program. You write an affine linear form on each wire. And for every path from input to output, you can look at the product of the polynomials or the product of the linear forms along that path. And that computes some polynomial. And then you sum this over all possible paths from input to output. That's your final output polynomial. Okay. Questions about the definition? Okay, so that's what a branching program looks like. So yeah, the final polynomial is the sum over all paths of the weight of the path, which is the product of polynomials along the path. And it's known, so if I define VF, be the class of polynomials computed by small formulas, polynomial size formulas of polynomial degree. VP is polynomials computed by small circuits. VBP is the class of polynomials computed by small branching programs. Then it is known, these inclusions are known, that formulas can be simulated by branching programs, the branching programs can be simulated by circuits. And I think there's a belief that all these inclusions are tight, but are strict, but we don't know how to prove it. We don't know general lower bounds for any of these models, or strong enough lower bounds. So it's a very, very interesting question to show that this inclusion is strict. And it's also it's a major open question to prove strong lower bounds for these models. I'll tell you what is known, and in the general models, very little is known. Okay, so the big challenge, I mean, some of you might have heard of the VP versus VNP question, which is the algebraic analog of the P versus NP question, which is to prove a super polynomial arithmetic circuit size lower bound for an explicit polynomial. But it's probably simpler to prove a lower bound for algebraic formulas or algebraic branching programs, because these are simpler models of computation. But it's also a big, grand, open question. And in general, the best lower bounds we know are only quadratic. Okay, so till very recently, there was this recent LSD breakthrough, which I will talk about, but till a couple of years ago, we knew, and we still actually, this is the best we know. For general circuits, the best lower bounds we know, and just let's set the degree of the polynomial computed to be n and the number of variables to be n, just to compare these results. For general circuits, the best lower bounds we know are of the form n log n. And for formulas and branching programs, we know lower bounds of the form n squared. And for bounded depth, there was a lot of attention on focusing on bounded. So it was hard to get lower bounds in general. And then you impose further restrictions on the circuit. Like let's make the circuit bounded depth, or let's make the circuit multilinear and notions of that. And the best lower bounds we knew until quite recently for various restrictions. I don't want to go through this list, but I want to just mention that till 3 years ago, we didn't even have depth 3 lower bound, strong enough lower bounds for depth 3 circuits. With further restrictions like homogeneity or multilinearity, we knew exponential lower bounds. But for depth 3 circuits, we just knew cubic lower bounds, and depth 4 onwards, we basically knew no lower bounds. And so this breakthrough from a few years ago by Nutan, Shrikant, and Sebastian gave the first super polynomial arithmetic circuit lower bounds, which work for all constant depth. And this was, it really, I mean, there were people working just on depth 3 circuit lower bounds, like improve n cube to n cube, anything better than n cube. And there was lots of sort of incremental work. But this was like in one swoop, it gave it for all constant depth, and it's a really beautiful result. And it turns out, they proved the results only for constant depth circuits, but constant depth or these bounded depth circuits are already very, very interesting. And you don't have to parse this slide fully, but we know very nice depth reduction results, which show that if you can get strong enough lower bounds for bounded depth circuits, or strong enough lower bounds even for depth 4 arithmetic circuits, this will separate VP from VNP. So it suffices to get a full understanding just of depth 4 circuits, for instance, because general circuits can be squashed into depth 4 circuits without too big a blow up. And so there was a lot of attention focusing on understanding constant depth circuits better. And now we have the first super polynomial lower bounds. It'll be nice to get exponential lower bounds. We don't have those yet. Okay. So let me tell you a little bit about how this LST proof works. A key ingredient in their proof of lower bounds for constant depth circuits is to first prove lower bounds for constant depth set multilinear circuits. So set multilinear circuits will play a active role in the rest of this talk. So I will motivate what these objects are. Okay, so I will talk about set multilinearity, why it's interesting. And we'll talk about set multilinearity in the context of bounded depth circuits, in the context of formulas, and in the context of branching programs. And in all these models, the set multilinear restriction is very, very interesting. And then we'll talk about lower bounds for set multilinear branching programs. Okay, so what's a set multilinear polynomial? So think of a polynomial in there are d sets of variables, x1 to xd. Each set might have n variables within it. And a set multilinear polynomial is a polynomial where each monomial in the polynomial picks up one variable from each set. Okay, so the determinant is a set multilinear polynomial because you can think of the n by n determinant. Each column is its own set, the variables in each column, and now each monomial in the expansion picks up one variable from each set. Okay, so questions about the definition? It's good. So here's a nice example of another set multilinear polynomial, the IMM, or the iterated matrix multiplication polynomial. You get the product of D matrices, D n by n matrices, and you can look at the 1, 1 entry in the product. Then these matrices are all variable disjoint. They're n squared, x1 variables, and n squared, x2 variables, and so on. And each monomial in the output picks up exactly one variable from each set. So this is an example of also a nice set multilinear polynomial. And this IMM polynomial we'll talk about a fair bit. So let's remember what this is. It can be observed that this polynomial can be also computed by a small branching program. So if you have B matrices, you can think of B layers in the branching program. So the edges going between the first layer of nodes and second layer have variables only appearing from x1. The second layer has variables only appearing from x2. The last layer has variables only appearing, and the product of these matrices can be seen as easily.
You can draw it if you want.
Let's draw it. So let's connect the ijth layer here. So suppose this is the x1. These two layers are using the x1 variables. Let's look at the ijth entry of the x1 matrix, and you connect the ith vertex here to the jth vertex here. And you have these such layers, and now you're looking at the 1, 1 entry in the product. So you look at the last layer, and you can look at the first vertex here and the first vertex here, and if you go through this branching program, it exactly computes the product of these matrices. So it's a complete bipartite graph, each layer, and the ijth entry in the byproduct in that graph is exactly the ijth entry of this matrix. So there's this efficient, it can be computed by a branching program. In fact, every branching program can be written as the product of matrices, can be expressed, the output.
So you have linear forms in there.
So if you have linear, So if you have linear forms appearing on the edges of this branching program, it will corresponding to linear forms being the entries of this matrix. Each entry of every matrix is a linear form. Good. So this IMM polynomial is very natural when you think about branching the model of branching programs. So that's an example of a set-multilinear polynomial. Even, like I said, the determinant and the permanent are also nice examples of set-multilinear polynomials. In fact, most lower bounds that we know today for different classes of algebraic circuits, the hard polynomial is often either the determinant or the permanent or IMM. There's the Nissan-Wigderson family of polynomials, which has recently also shown up in lots of proofs, and they're all set-multilinear polynomials. So set-multilinear polynomials just show up naturally. Even if you're not studying set-multilinearity explicitly, most examples of these hard polynomials people study are just naturally set-multilinear. So you can talk about when you're trying to compute a set-multilinear polynomial as output, say the determinant or the permanent or the IMM, your underlying circuit need not be a set-multilinear circuit. Along the way, you might compute polynomials that are not set-multilinear, and they might cancel out monomials somehow, and eventually the output is set-multilinear. But if you, in addition, impose the constraint, a restriction on your model of computation, which says that, look, I want to compute a set-multilinear polynomial as output, but I want every intermediate node of the computation to also be a set-multilinear polynomial, then that's a further restriction I have imposed. And so you can talk about the class set-multilinear VP, which is the class of all polynomials computed by small circuits, with the added restriction that each intermediate node is also a set-multilinear polynomial. You can talk about set-multilinear VF, you can talk about set-multilinear VBP. So the intermediate computation has to also be set-multilinear, and set-multilinear with respect to the same original global partitioning of variables that was decided in the beginning. So you can talk about these classes, and we will talk about all these classes too. So now let's see, why is set-multilinearity interesting? First, let's see why it's interesting for bounded depth circuits. And so this brings me back to this LST result, where LST, they showed lower bounds, the first super polynomial lower bounds for general constant depth circuits. So the first step in their proof was the following, that if you have a constant depth formula or circuit, it doesn't matter when it's constant depth. Suppose the size is small, the degree is d, and the depth, think of delta to be a constant. So you have a constant depth circuit of small size, computing some polynomial. You can take this circuit and massage it into another circuit, computing the same polynomial. But now that circuit of formula is a set multilinear formula. But now you blew up the size of it. You blew up the depth a bit and you blew up the size a bit. But the new circuit of formula that you got, it's computing the same polynomial, but it's now become set multilinear. So each intermediate node is computing a set multilinear polynomial.
D to the D is not so minor.
Yeah, good. So let's look at what this big blow up is. S to the O of 1, fine, it's just a polynomial blow up. Let's not care about it. D to the D is pretty severe. And the depth of the circuit blows up by a constant. Let's not care about it much. The D to the D is the most severe part of this, which is, again, so it's very prohibitive unless you think about the degree to be very small. So the degree is something like log n over log n. If everything is poly and size and invariant, if the degree is tiny, log n over log n, then this is just a polynomial blow up. So the observation was that for these small degrees, if we prove a set multilinear formula lower bound in that setting, then it would imply a super polynomial lower bound in the general setting without the set multilinearity constraint. So this reduction is actually not that hard to go from general formulas to set multilinear formulas. It's one has to be careful, but it can be done. What was quite non-trivial about LST was then to prove these strong enough lower bounds for constant depth set multilinear formulas, especially when the degree is so tiny. It gets harder to prove these lower bounds when the degree is tinier. And so that's what they did. So they proved lower bounds of the form n to the d to the some constant for the model of set multilinear formulas. And now even when d is like log n over log n or something, this is still super polynomial. So their main focus was prove strong lower bounds for set multilinear constant depth circuits, and this allowed them to prove lower bounds even without set multilinearity. And I just want to point out that such a set multilinearization result that LST used from general constant depth circuits to set multilinear constant depth circuits, such a set multilinearization was known with a similar kind of blow up by an earlier work of Raz, but it did not focus on the constant depth setting. In the unbounded depth setting, this was shown by Raz. So we already saw why set multilinearity is interesting for bounded depth circuits. Let me tell you a little about set multilinearity and formulas. So Raz showed something like the following, very similar to the LST result. If you have a size S degree D formula, then you can convert it to a slightly blown up set multilinear formula. What's the blow up in the size? It's a polynomial blow up if the degree is small. So if you think of S to be poly n, again, same. If the degree is log n over log n, this blow up is only a polynomial blow up. And so if in the setting of degree being at most log n over log n, you can prove a super polynomial lower bound for set multilinear formulas, then it would prove a lower bound for general formulas. And that would be a pretty big deal. We know nothing like that.
So the difference here is that the depth is not preserved?
Yes, the depth is not preserved. So when you start off in using this Raz as a result, we just started off with at least this result, the way I've stated it, you start off with constant depth. The new thing may not be constant depth anymore. It might blow up the depth further. And LST did it carefully to make sure that the depth is preserved. Yes.
Were all the results so far for formulas only?
In the constant depth setting, the LST setting, circuits and formulas, I'm going to use interchangeably almost, because you can go from one to the other with a small blow up, with a polynomial blow up in size. So in the constant depth setting, I will not care about the distinction. But for this Raz's work, it matters now that this is a set multilinearization holds for formulas. Because in the unbounded depth setting, it starts mattering, whether you're talking about circuits or formulas. Okay, so good. So we do care. So set multilinear formulas are really interesting. And they're especially interesting if you look at them in the low degree regime. Because if you can prove super polynomial lower bounds for set multilinear formulas in the low degree regime, that gives you lower bounds for general formulas. Okay, so set multilinear formulas are hence an object definitely worthy of attention and study. Let me try to convince you that set multilinear formulas can also be interesting in the high degree regime, not just in the low degree regime, for the following reason. Suppose your hard polynomial is the IMM polynomial, iterated matrix multiplication. So let's try to study set multilinear formula lower bounds when the hard polynomial is IMM. There was a second paper by Nutan, Srikanth, and Sebastian who studied this. And let me tell you why it's interesting to study. And the one reason is that the IMM polynomial, the best formula we know for computing IMM is a simple divide and conquer approach. To compute the product of D matrices, you'd compute the product of two, the first two, then the second two, then the next two, and then you made the product of D matrices became a product of D over two matrices, and then you iteratively do it. And some divide and conquer approach gives you a formula of size n to the O of log D for the product of D matrices. And this is the best we know. This is the best formula we know. Good. So in general, this means that if you want to compute a product of n matrices, we can use products for if so, and D is much smaller than n, we can use a formula of IMM for products of D matrices as subroutine, and then you can build upon it to get the product of n matrices. So if we can have or very efficient formulas for the products of D matrices, we can put this all together to get an efficient formula for the product of n matrices. In particular, if you can prove the optimal lower bound for a product of n matrices, it will imply an optimal lower bound for the product of D matrices for D smaller than n. Because you couldn't have had a very efficient algorithm for D smaller than n because it would have given you a really efficient algorithm for D larger than n.
So the previous lower bounds that one had for determinant, let's say for set multilinear formulas for the determinant, they're of this form, n to the log n, but you don't have this structure, so they don't imply any.
Yes. Yes, it's not, the self-reducibility property doesn't hold. If the hard polynomial was IMM, then that would have been, then you could have used this, factor I'm telling you, and you'd have gotten general formula low ones. Yes. Good. I'll come back to this Rand. I don't think Rand proves n to the log n for the determinant, but I will. For the determinant?
Yeah.
Okay. Okay, so I'll.
It's n to the log n.
And it's not log.
It's definitely.
It's n to the log n?
Yeah.
So the proof, it's using partial derivatives, right? So it doesn't give anything.
It doesn't use partial derivatives.
Let me come to, let me come back to that. Okay, so anyway, so if the hard polynomial is the IMM, then it would have major consequences. So even for large degree, if you study set multilinear formulas and your hard polynomial is self-reducible, then that's great. Good. Good. So it's worth studying these strong, the optimal set multilinear formula lower bounds for these polynomials. And then LSC, in this follow-up book, they try to, when the hard polynomial is the IMM, they manage to prove not the optimal n to the log n lower bounds, but they manage to prove log n to the log n lower bounds. So if you can improve this base log n, if you can improve it to n, then it will imply general lower bounds.
So this weaker thing doesn't imply anything about general formula.
It does not imply
No.
anything about general formulas because you truly, we want to prove it for such small degree, you want to get these lower bounds, you need to get truly, I don't know, maybe n to the log n, something slightly worse would give it to you, but log n to the log n is definitely not enough to give anything meaningful for the low degree setting.
If you would prefer combinatorial analogy, is the same as formulas for connectivity, SC connectivity. Right, so the obvious, and log n, the same one. And if you prove this, then you will, immediately see that if you want to just, I promise you that the distance between S and T is some number, but bigger than a constant. You will be able, you will rule out a polynomial side for that. It's the same with them.
Okay, so we're trying, so the goal is, let's prove these optimal lower bounds as we can for set multilinear formulas and try to make the hard polynomial IMM. And in fact, we're talking about these optimal lower bounds for set multilinear formulas. We don't even have we didn't have optimal lower bounds even for bounded depth set multilinear formulas. Even if you didn't care about IMM, even for other hard polynomials, we did not know these truly optimal lower bounds. LST got log n to the root log n for depth 2, again, for the IMM. It's a very interesting question to get n to the root n, even if you're not doing it for general formulas, even for depth 2 formulas. Can you get the best possible you could get for IMM, which is n to the root n? Can you do it? And we don't know how to do it today. And you can ask the analog for any constant depth, of course. Like, what's the best upper bound for IMM and the best lower bound for IMM? They don't match. And so a couple of years ago in joint work with my student Deepanshu, we were studying this problem of what's the best lower bound. Can you prove these optimal set multilinear lower bounds? You can ask it for general formulas, but you can even ask it for constant depth formulas. And these optimal like lower bounds we were able to prove, but not for the IMM. We were able to prove it for some other polynomial. What that polynomial is, I'll talk about. It's an interesting polynomial. But we can't do it for the IMM. That polynomial that we can get, we're able to get a polynomial which is in set multilinear VBP. We're able to find a polynomial sitting in set multilinear VBP. I will talk about that. And for that polynomial, we can get the best possible lower bounds you could hope for in the constant depth setting and in the unbounded depth setting also. A set multilinear, so let's unpack this. Like, what is set multilinear VBP? Why is that not the IMM? Okay, so what is the hard polynomial? We first showed our results for the easiest hard polynomial we could find, which was the Nissan-Wigderson design-based family of polynomials. And then we said, okay, now we have a handle on it. We can prove our low bounds for one class. We just have to make that hard polynomial simpler and simpler and simpler till we get it to the IMM. And I'm aware of at least 2 classes of lower bounds and arithmetic circuits in the past where it was much easier to prove it for these NW polynomials, and with harder work, it was shown to hold for IMM. So at some point we were optimistic that we just have to analyze the complexity of IMM really well and we can prove these lower bounds for IMM. But we were not able to. We managed to get a hard polynomial lying in set multilinear VBP. And to do that, we adapted techniques from Zev's work from separating multilinear branching programs and formulas from a while ago. We took that, understood that, reworked some parts of it to make it work in the set multilinear setting as well. So we can make a hard polynomial sit in set multilinear VBP. And now, so this is a branching program, a set multilinear branching program. That's where our hard polynomial sits. And you may ask, isn't the IMM kind of complete for branching programs? So why aren't we done? So now I have a hard polynomial, which is a branching program. Every node computes a set multilinear polynomial. You can write that branching program as a product of matrices. And now, do these matrices have this self-reducibility property? Turns out we don't know, and we don't think so, because the problem is that these matrices may not be variable disjoint. So the IMM polynomial, the IMM, when I said had this self-reducibility property, the product of n matrices, you can compute by using algorithms for computing products of fewer matrices at the time. That IMM polynomial was the product of variable disjoint matrices. The hard polynomial that we get will still be set multilinear. Each intermediate node will still be a set multilinear polynomial, but the linear forms, for it to truly work, I needed the variables here to be disjoint from the variables here to be disjoint from the variables here. And the hard polynomial we get is some weird polynomial where the variables get mixed up inside. It's still true that every intermediate node is set multilinear. Whatever comes from Zev's paper with arc partitions and all of that, we take that and we construct these polynomials, but it's not variable disjoint. Because it's not variable disjoint, we don't get general formula lower bounds. So now a very interesting question is that what is the gap between these two models? Set multilinear branching programs where every node computes a set multilinear polynomial, or this nicer model of set multilinear branching programs, which is layered. The first layer has only variables from one set. The second layer has variables from the next set. The third variable has third layer has variables from the third set, etc. So there's a nice layering of the branching program and separation of variables. We really want the hard polynomial to be that, but we don't get it. So, right, I can define this other model, ordered set multilinear branching program. So your polynomial with d sets of variables. If your branching program has d layers and there's a permutation on those d sets of variables, and the ith layer only contains variables from the ith permutation of a permuted set, that would be great if our hard polynomial lies in this model. But so it's a very interesting question to understand the relative complexities of these two models, set multilinear branching program and this ordered set multilinear branching program. And if these two models were the same or similar, you can go from one to the other, this would give us general formula lower bounds. But in the current work, we study the complexities of these two models and show that they're actually quite different. You can find a polynomial which is computed by a small set multilinear branching program. But if you want to compute it by an ordered set multilinear branching program, that needs to be really large. The size has to be maximally large, n to the d, which is as large as you can hope, the strongest possible over. So these two models are quite different. Questions? Okay, so set multilinear branching programs are also an interesting object. We want to understand ordered versus unordered and get lower bounds for strong enough lower bounds for set multilinear branching programs when the hard polynomial is IMM. Let me tell you another very interesting, while we were working on understanding set multilinear branching programs, just last year there was another very beautiful or interesting result that came out by C.S. Bhargav, Pratik Dwivedi, and Nitin Saxena. And they proved a result which was like the LST set multilinearization for constant depth formulas, and then Raz had it for formulas. BDS showed a set multilinearization for branching programs. A very analogous result. So they showed that if you have a degree D polynomial, an n-varied degree D polynomial that you can compute by a branching program of size S, then you can take that branching program and set multilinearize that branching program. And you can compute that polynomial by a slightly bigger branching program, which is now a set multilinear branching program computing the same polynomial.
This is all. No?
So yeah, good. So now let me explain what the model is. That slightly bigger branching program is an ordered set multilinear branching program, but it's a sum of ordered set multilinear branching programs. So one ordered set multilinear branching program gives you one ordering. The first, we take one permutation on the D sets, and that's one ordering, and you can take a branching program in that ordering. Now you can take a different ordering of the sets, and you can take a branching program in that ordering. And then you sum these two branching programs, that's still a set multilinear branching program, because every intermediate node is still set multilinear. But it's a sum of two, together they're not an ordered branching program. It's just a sum of branching programs in two different orders. So this is some kind of intermediate class between ordered set multilinear branching program and set multilinear branching program.
Is it sum of just two or like?
Good, so no, unbounded sum.
Polynomial, or whatever.
Unbound, d to the d. The final size is d to the d times s. So the number of summations can be something like d to the order d. Okay, so so if d is small, you get a polynomial computed by a branching program in this class, which is just a polynomial blow up in size.
But this to the D means you might as well use all permutations, right?
Might as well use all permutations, exactly.
Like de facto, yeah.
This is de facto. This is essentially de factorial.
The number of steps is D.
Oh. Wait, so I see. Is this supposed to be easy? No.
The proof is not hard. It's not yet not so bad. It's not trivial. You first homogenize. It's a little bit of careful stuff, but it's quite. All these set multilinearization, even RAS and LST, they're all actually inside. The proofs are not hard. All the D to the D blow-ups are like some brute force over all possible subsets, and once you're willing to lose a factor of D to the D, it's not. It's a one-page proof, half a page proof. So here, this D to the D is all permutations. So you can take your branching program which had mixed up, but it may not have been set multilinear at all. The original branching program could have been, you're not saying I'm starting with a set multilinear branching program and unraveling it as a sum of ordered. You're starting with a branching program which may have no set multilinearity within it at all, but you're still able to unpack it as a sum of ordered set multilinear branching programs. And you might see all de factorial orderings. But you can still, if D is smaller than log n over log n, this is a polynomial blow-up. And for this model, you can still hope to say that I can prove this, the best lower bound that you could prove. If you prove optimal lower bounds for this model, you can hope to prove super polynomial lower bounds for this model, even when D is log n over log n. And that will give general branching program lower bounds. It will give super polynomial lower bounds on the determinant, which is complete for branching programs. So understanding, so this class now sits between set multilinear branching programs and ordered set multilinear branching programs. Because it is not one ordering, it's a sum of orderings, but together they sit within, this whole class is within set multilinear branching programs, or set multilinear, or VBP that I call it. So this class is very interesting. So we started looking at this class. Can we prove super polynomial lower bounds? Or what is the best lower bound we can prove for this class? And we want to get lower bounds in the low degree region. So for low degrees, can we prove super polynomial lower bounds? And ideally, we want the degree, if we can make the degree log n over log n and still get super polynomial lower bounds, then this gives you general branching program lower bounds. So what we are able to do, our main result is we get lower bounds in this model, but we only get it for degree little omega log n. So if you have a polynomial of degree, I don't know, 100 log n, then we can get lower bounds of the form n to the some constant, depending on 100. So that's basically the main result. You want to make the degree as small as possible, and still get super polynomial lower bounds, and we get it manage to get the degree as low as log n, and still get such lower bounds. For larger degrees, if you unpack whatever parameters are there, we can get exponential lower bounds. And what is our hard polynomial in these lower bounds? It's easiest to do it for a polynomial in V and P, the Meson-Wigderson family of polynomials, but with a further hard work or a lot more hard work, we can make the hard polynomial in set multilinear ABP, which is sort of like bad news because you cannot, if you want to truly set branching programs lower bounds, your hard polynomial should not be computed by a branching program. So if you want to go to degree less than log n over log n, this cannot be the hard polynomial. But when for degrees here, we are able to make it the hard polynomial branching program, in fact, a set multilinear branching program. Okay, so I will quickly tell you a little bit about what the related work is and then give you some flavor of what goes into the proof of the lower bounds. So for a single ordered set multilinear branching program, this goes back to the seminal work by Nissan, I think, which started the method of partial derivatives to prove lower bounds for circuits. And Nissan proved exponential lower bounds on the width of the number of, so for a single ordered set multilinear branching program, that's exactly the model that he studied. And he showed that there is a hard polynomial so that if you have any single ordered set multilinear branching program, computing it, one of the layers needs to have a lot of vertices in it. So the width, there's some layer which has width exponentially large. So then the sums of ordered set multilinear branching programs, and there are not many works which study this model. Arvind and Raja showed an exponential lower bound when the number of summans was small. So with t summans, the lower bound was 2 to the n over t. And the Bhargav, Dwivedi, Saxena paper, which proved the set multilinearization result, they showed that if you restrict if you force each layer to have small width, n to the little o1, then you can prove exponential lower bounds. But for unbounded widths, their paper did not give any lower bounds. And so, but we are able to get, again, unbounded, no constraints on the number of summans, no constraint on the width, we are able to just get the lower bound outright. There's another interesting work, which is quite related to what I showed as a work by Ramya and Rao, which study multilinear ROABP lower bounds. So I don't want to unpack this too much, but multilinear ROABPs are pretty related to set multilinear branching programs. And if you look at this result, it implies, and you homogenize in a careful way, it gives you lower bounds for this model in the setting when t is very large, when d is very close to it. All the sets are very small. But doesn't tell you when the degrees, in the setting where n is large and the degree is small, it doesn't give you something. Yes.
Could we go to the previous slide? I think I'm getting some parameters crossed up in the
Yes.
second result.
Yes.
So what is I thought the number of summons was d to the d or d factorial.
That's in the set. So any branching program, if you want to set multilinearize it, you will get this d factorial blow up.
Okay.
Here, D is the permanent, D is N. So it's,
That's specifically for the permanent.
Now for this one, for this one hard polynomial, right, we want to prove lower bounds. Conceivably to compute the permanent, you will need n factorial summons.
Yeah, I understand.
But this paper is able to show that as a lower bound, that if you want to compute it with t summons, the size needs to be.
Oh, I understand.
Yeah.
2 to the n upper bound for the permanent is not for ABPs, it's circuits.
2 to the up, the riser's formula. It's probably a branching program. It doesn't contradict this, right? It might be a.
No,
Yeah.
it's not factorial.
It's a you can get a 2 to the n upper bound also for the permanent, I think, with branching programs. Yes. Right, riser's formula gives you 2 to the n upper bound.
yeah, it's a formula.
It's a
So it's suddenly
Yeah.
an ABP.
yeah. Good. So let me tell you a little bit about the proof. So how do we get lower bounds for sums of ordered set multilinear branching programs? And the proof is actually not that hard when you in hindsight. So it's using the notion of complexity measure that has been studied, or a variation on the very classical notion of complexity measure. So how do we prove lower bounds, or how most of the lower bounds been proved? You come up with a nice measure of complexity for polynomials, show that your hard polynomial has large complexity, and show that your underlying circuit class, the complexity of the class is small if your input circuit or whatever object from the class is small. And so if you have a formula or a branching program computing NW, the complexity of it needs to be large, and so that branching program needs to be large. So I'm going to use a variant of the partial derivative measure, which was introduced first by Avi and Noah. So, and the LST proofs used a variation of this measure. This is the second LST work. Our work is some hybrid between the Nissan-Wigderson measure and the LST measure, but it is also like Raz's measure for multilinear lower bounds. So anyway, let me describe completely what the measure of complexity we use is. So we have D underlying sets of variables. And what we'll do is we'll take these D sets of variables and randomly partition them into two parts. So to each set, I'm going to assign either a positive sign or a negative sign. And I will do this uniformly at random for each set. So this gives me a random partition into two pieces, the positive half and the negative half. So I look at all the index sets that are in the positive half, and I call that the set P. I look at the index sets which got assigned a negative sign, and I call those indices in this the negative set. And I look at all monomials or set multilinear monomials over the positive indices. I look at all set multilinear monomials over the negative indices, and I construct the following matrix. The rows of the matrices are indexed by all set multilinear monomials coming from the negative sets. The columns are indexed by all set multilinear monomials coming from the positive set. And the ijth entry, I look at the corresponding monomial from here, the corresponding monomial from there. I look at their product. It gives me a set multilinear monomial overall. And I see, does it appear in my final output polynomial? And if it does, whatever the coefficient is, I write that in the ijth entry. So it's a coefficient of mi times m. So if we look at m1 here and m2 here, the coefficient of m1 times m2 in my final output polynomial, I write it there. And the rank, and now I look at this big gigantic matrix, and the rank of this matrix is the complexity measure we will be looking at. Okay, so that's my complexity measure. This is the complexity with which this measure I will analyze the hard polynomial. With this measure, we will analyze sums of these ordered ABPs and try to show that ordered ABPs, sums of ordered ABPs have low complexity. And again, this is the measure using the LST1 was deterministic, was similar measure for set multilinear polynomials, but they didn't have a random partition into two sets. It was deterministic, and they played with sizes of the different sets of variables to get their bound. And then they had a follow-up work which used a randomized measure, but there's a variation on our measure. This measure is actually really the simplest, or nicest measure we could think of, or cleanest measure, which was very similar to the measure used by Avi and Noam when they studied constant depth, I think depth-free circuits, along with random restrictions. And Raz Yehudiyov used a version of this measure for not when the setting is set multilinear, but multilinear. Okay, I'm going to have more math notation, so I switch to my PDF's handwritten slides. I'm going to finish the rest of the talk using this. Let's see. Can I open?
It's on a full screen.
How do I make it full screen? View.
Yes.
Full screen. Perfect. Okay, so then I have, so now what I did was I picked a so this was the complexity measure. I picked a uniformly ±1 string of length d. And that string tells me for each set between x1 to xd, whether it goes into the positive or the negative set. And then I got these positive index sets, negative index sets, and I constructed this matrix. You could, the measure, complexity measure could be the rank of the matrix, or you could normalize the measure by a certain constant to make it the rank at most 1. It won't matter. I will mostly just talk about the rank of the matrix. Yes.
Why is it called a partial derivative measure?
Good question. So if I looked at the final output polynomial and I took partial derivatives of that polynomial with respect to these monomials, then each row of this matrix would correspond to the coefficients of the partial. So the first row would correspond to the coefficients of the different monomials when you take the partial derivative with respect to this. The second row would correspond to look at the polynomial when you take the partial derivative with respect to the next monomial, and so on and so forth. So I don't know if in the original works they were called the partial derivative matrix, but since then,
Yeah, we call
You called it the partial derivative?
derivative. This is the
Yeah.
the rows are polynomials in the M2 variables, in the positive variables, right? So you are looking at the dimension of all partial derivatives with respect to the negative one. It's the same with
you take partial derivatives with respect to all each row is a certain polynomial, which you get by taking the partial derivative with respect to one of the monomials in the negative set. And you look at all these different partial derivatives, these polynomials, which are the partial derivatives with respect to different monomials, and you're looking at the dimension they span.
If you don't partition the variables, you just take the set of all partial derivatives of, let's say, a multilinear polynomial. Then unless your complexity measure, then it's really simple to see that it's subadditive under plus gates, under linear combination, some multiplicative under multiplication. So it combines very nicely with the computation of an arithmetic block. And the rank has similar properties.
Okay, so this, like Avi was mentioning, this complexity measure, if you normalize it, then the measure is at most 1. But forget the normalization, forget that this point for right now. But this measure is subadditive, and it's exactly multiplicative if f is g times h and g and h depend on disjoint sets of variables, then it is exactly multiplicative. And it is subadditive. And I'll use these properties to bound the complexity.
So actually, I got a bit confused. Why is it at most 1? I mean, the rank can be as large as the smaller.
Normalize.
If I normalize by the number of rows times the number of columns and the square root, the rank is at most the smaller of the rows and
Right,
columns.
okay.
And
It's the right direction. Okay.
It's the right direction. I think what I'm going to talk about, let's not care about the normalization. Let's look at the overall rank, which is at most n to the d over 2. For the d over 2, at most d over, each one of the sides has at most d over 2 sets, and the number of monomials is at most n to the d over. Okay. And how many minutes do I have it?
At least 10.
Anyway, I'll leave it to go over maybe all of the proof. Okay, so for any subset of the indices, we can look at each index for a +1 or a -1. For each subset of the indices, we can sum the pluses and the minuses, the +1, -1s on that set. And we can talk, if the sum is 0, then that set has no bias, the equal pluses and equal minuses. But if the sum is, large in magnitude, that means you have more pluses than minuses or more minuses than plus. So this quantity measures the bias restricted to the coordinates of a set S. And for any polynomial f, the rank of this big partial derivative matrix is, if the bias was 0, then the rank is at most n to the d over 2. But if the bias is larger, that means you have more positive sets or more negative sets, then you'll lose something in the rank. It won't be as large as n to the d over 2. You lose some quantity depending on the bias. So you get n to the d minus whatever the bias, overall bias is, divided by 2. Okay. Let me, to say how our proof works, since the final statement generalizes Nissan's lower bound for a single ordered set multilinear ABP, let me quickly recap Nissan's proof, and then we'll see how to modify it to work for some gates as well. So Nissan's original lower bound was the following. So you take a hard polynomial, which is full rank for all possible ways of partitioning the index, these D sets into two parts. As long as you partition into equal plus positives and equal negatives, the rank is maximized. Take any such polynomial, the rank will always be very large. Now take a single ordered set multilinear ABP A with some ordering coming from some permutation sigma, which computes the polynomial. And I want to show that the rank of the rank of this, or the complexity of this ABP is small. Now I can pick my partitioning into two, the left set, the negative sets and the positive sets after looking at this ABP. I take an ABP computing the hard polynomial, I pick a nice word which will show me the separation in complexity. And the nice word that I pick is, so I have an ABP computing a polynomial, I'll take the D layers, I'll take the first D over 2 layers and I'll make it the positive set, and I'll take the next D over 2 layers and I'll make it the negative set. So your ABP looks like this, and I cut it along the middle, and all the variables that come to the left are the positive set, everything that comes later is the negative set. And now the final polynomial computed, let's look at the polynomials computed along the S vertices in this middle layer. Suppose F1 is the polynomial computed from here to here, and G1 is the polynomial computed from here to here, then this is one path I can take in the ABP, and it's not hard to see that the final output looks like F1 G1 plus F2 G2 plus F3 G3 through FSGS. So I want to bound the complexity of this. It suffices using sub-additivity of this rank measure. If I can bound the complexity of F1 G1 and of F2 G2, etc., I can then bound the complexity of this big sum. And it's if all the left vertices. So, okay, so now what's the rank of F1 G1? Or the complexity of F1 G1? It's the complexity of F1 times the complexity of G1, since they are variable disjoint. But this matrix F1 is not a square matrix at all. It's a completely flat matrix. It's a rank 1 matrix because the positive negative split was not an equal split at all. So it turns out that F1 G1 has rank 1. F2 G2 has rank 1. And so the overall big summation has rank at most S if there are S vertices in the middle there. And so the rank of this single ordered set multilinear ABP is at most S, but the final polynomial had rank something like n to the d. So S needs to be at least n to the d to compute our hard polynomial. And that's Nissan's proof. So it was a really clever complexity measure targeted to this setting. Let me give you a slightly different proof of Nissan's result, which will guide the proof in the direction that I wanted to go. Let me give you a variation of proof, which gives a slightly worse bound, but we'll see why it's nicer. So the proof that I gave you, it said, let's look at the ordered set multilinear ABP and decide which sets to will get positive index and which will get the negative index. Now let me do the same thing by just picking a random plus minus 1 partitioning of the variables and see that a random word gives me a low bound. But I'll pick a random word conditioned on the overall bias being 0. So random with the equal number of pluses and equal number of minuses. So my hard polynomial still has maximal rank. But let's see, for a random word, does a single branching program get small rank? So now if you look at the left half, it's not all pluses. It's a random plus minus 1 word of a string of length d over 2. The expected bias of a random string is at roughly square root d. So with constant probability, you'll get square root D bias here, square root D bias there. And that's enough to say that there's some rank deficit. These matrices will not be squared, and we'll get a loss of n to the square root D in the rank of the matrix. We get a loss of n to the square root D here, we'll get a loss of n to the square root D there, and overall there'll be an n to the square root D loss. So we don't, so the final big polynomial that you get, its rank will be this maximal rank minus omega square root D in the exponent. And using then sub-additivity of these F1 G1 plus F2 G2 plus F3 G3, we're summing S polynomials, the total rank is at most S times n to the D over 2 minus omega square root D.
The same idea used by Ran, it's the formula.
It's very similar lower bound used by Ran formula for the random partition,
Yeah.
exactly. And so it gives you a slightly worse bound, but you didn't have to look at the ordering of the ABP in order to compute your to determine your complexity measure. So now can you use, since you don't have to look at the ABP to compute the complexity measure, it didn't matter what the ordering of the ABP is. Suppose you had a sum of ABPs in different orderings. What can you do then? I will bound the complexity of each AI. So my final ABP is a sum of ordered ABPs. Each AI is an ordered ABP, and I have T summands. If each AI has low complexity, then the total sum has low complexity because it just has complexity T times the complexity of each AI individually. That's great. But we're not quite done for the following reason. So what we just showed was that each summand here, with constant probability, you'll get some rank deficit. I said the bias in each half was square root D. But you only get that large a bias of square root D with constant probability. So in order for, so each summand with only constant probability has this rank deficit. If I want to say that each summand has rank deficit and I want to union bound and say that every summand has rank deficit, then this constant probability is not good enough. It will allow me to only handle T, which is constant. Yes? So if T was small, then by a union bound, you could say that, okay, each summand has small rank, and so there exists a word which makes each AI small rank, and then the rank of the sum is at most T times the rank of each individual piece. And we get an extra factor of T, which is insignificant really. But so we need to, this constant probability was not good enough. We need to amplify the probability. And one way of amplifying the probability is saying, look, let me not ask that each half has bias square root D. What if I just care about, I don't want to get such strong exponential low bounds. Let me just start with hoping for weak bounds. What if I just want to say that each piece, each half has bias 4th root of D? Now it's not just a constant probability of a piece having bias 4th root of D. Maybe there's this, with probability closer to 1, you will be able to guarantee smaller bias. And so you'll be able to take a union bound over more summands. So you can try this, and you can try fiddling around with what parameter put here. But even then, it's easy to show that you can't go beyond D summands. Because if you take any ordering, any permutation, and you take the D cyclic shifts of that ordering, then for one of the cyclic shifts, you can find there'll be 0 bias. And so you can find you a sum of D orderings where one of the pieces will have 0 bias, and if it has 0 bias, none of this proof will not go through. So just playing around with bias on 2 halves will not give you the bound. So this is the next idea that we tried, which actually works. Instead of cutting the ABP into 2 pieces down the center, let's slice it into multiple pieces. So let's see what happens when we slice it into 3 pieces. So you take one, so you have D layers, you look at the first D over 3, then second D over 3, and last D over 3. So you have 2 slices you're making. So you have S vertices in the first slice and then another S vertices in the next slice. And so your output polynomial first was just sum over Figi with S summations. Now you have S square summations and you'll get something like Figi Hi. Where each of these depends on D over 3 variables, D over 3 sets of variables. And you can try that, and then again with some constant probability. I mean, you can now you lose an S square instead of an S in the number of summands. So where did you really gain? You don't explicitly see where you gained here when you just cut it into 3 parts, because you still get bias. It doesn't work out, but let's cut into a lot more pieces. So just cutting it into 3 pieces. Let's see what happens if we cut it into here's a setting of parameters, square root D pieces, each of size square root D. So already here you will start seeing where the gain is coming. To get the optimal bounds, we will tweak these parameters further. But let's just see why square root D pieces of size square root D gives you the improvement. So we have Q equal to square root D pieces. Each piece has R sets within it, and R is something like square root D. So when I cut it into so many pieces, my final output is a sum of products of polynomials. But the number of summations, or the number of summands I have, is S to the Q minus 1. It was 2 pieces, it was S, 3 pieces was S square, Q pieces I get S to the Q minus 1. So this S to the Q minus 1, I'm just going to give up on this. I mean, this is going to hurt my final calculation, the final rank bound. But fine, let's see what happens. So I have S to the Q minus 1 terms. Each term is a product of Q polynomials, where each of these Q polynomials is set multilinear over D over Q sets. So it's a product of square root D polynomials, each depending on square root D variables. And now I pick a random word, and if F1 depends on square root D variables, I expect the bias on F1 to be about D to the 4th. The expected bias. And with constant probability, there's D to the 4th bias. There's D to the 4th bias here, D to the 4th bias here, etc. So individually, just with constant probability, I can argue about the bias, but we can say that the total bias, the sum of biases over all pieces, which we expect to be, square root D times D to the 1/4. Using Chernoff bounds, we can say with exponentially close to 1 probability, the sum of biases will be large. For no individual piece, I can guarantee that. But on average, over all the pieces, with exponentially large probability, exponentially close to 1, that the sum of biases will be Q times square root R, which if Q was root D, R was root D, that's 70. Sum of D to the 3/4, which is polynomial in D. So the final rank, so then when the sum of biases is large, that's the rank deficit I get, because in each piece when there's bias, I gain something, that my rank falls a little. My sum of biases is large. Whatever the sum of biases is, that's how much the rank falls in the exponent. And now I lose an S to the Q because there were S to the Q summands. When I cut it into so many pieces, I lose an S to the Q. Now in the setting of parameters we had, Q was square root D. This is D, this is square root D, this is D to the 1/4. So this is already omega D. So an S to the square root D versus N to the D over 2 minus something that's much smaller than square root D. This turns out to be insignificant. I mean, this term versus how much you lost here, you lost much more than what you paid for. So you still get an exponential lower bound on what S needs to be for this to work on, and these bounds became, and now what you gained is you can union bound over, you can union bound over many summands, because there's a single word which will give you low rank over all of them. You can do a union bound argument because of the way because of the exponentially close to 1 guarantee of getting this rank deficit. And so that's all I want to say about the proof. So this is basically the whole idea.
You don't get into the D low bound.
We don't get into the D low bound. Into the D
You said you get a maximal low bound.
No, we don't get maximal not in this setting. There was a maximal in some other setting.
Okay.
Yeah. This, if you work it out, the parameters, we will get this, when D is omega log n, we get super polynomial low bounds. And if we got the maximal low bound, that would give branching program low bounds. So that would be awesome. So this setting we don't get. There was a different setting which I didn't talk about. Oh yes, with a single, I said there's a maximal separation when the hard polynomial is set multilinear ABP, and you have a single, not a sum of orderings. For a single sum, then you get the maximal ordering. But for a sum, we lose because this, and basically where we lose is this exponentially close to 1. The union bound over the many orderings, it doesn't work out. So that's all I want to say about the proof. We optimize the parameters to get the final statements to work. But the most interesting question, of course, is, I mean, the proof is not that hard. It is fairly simple. And where can we, are there ways of improving it to, first, I mean, nothing is going to, no barriers are broken. Nothing happens if you make the improve, I mean, there's scope for improving the low bound and not making it work just for degree up to log n, but log n over log n. It seems perfectly reasonable to that you just go and do some small tweak and you can improve the bounds.
But the Chernoff bound fails
Chernoff bound.
below log n.
Chernoff bound fails below log n. Exactly. Ultimately, we want to make the degree even smaller to log n over log n. That's the ultimate goal. But in the other direction, it could be like Reiser's formula for the permanent. We can make the d factorial into a 2 to the d. It helps you get a more efficient computation of the permanent. Maybe the set multilinearization of BDS can be improved to show that any branching program, when you set multilinearize, the blow up is not d to the d, but 2 to the d. If the blow up is 2 to the d, then this our result will in some sense be tight. At least when the hard polynomial is a branching program, you can't hope to prove a better low bound. So that's scope for improvement on both directions. Okay, so I will end there. I'm probably taking too much time already. Thanks.
Questions?
So we know for the determinant that there's no set multilinear formulas of size n to the log n, right?
Yeah,
That's on.
even multilinear.
Uh,
Even multilinear. You don't need set.
That's multilinear, right?
Yeah, even multilinear.
So if you could put the same thing for IMN, that would give some huge separation because it has this self-reducibility.
I'm a little bit confused about this determinant. I know the Raz Yehudev had another polynomial in VP, where they work very hard to get the n to the log n lower bounds for multilinear formulas, computing this polynomial in VP. This determinant thing, I'm not sure the n to the log n is known for the determinant as is. I don't.
It's just
I think-
Ron's papers, determinant and permanent.
I think that might be multilinear VP.
But determinant is not, is set multilinear, right?
Right, but
But it doesn't have a multilinear
Circuit.
Perfect. We don't know multilinear circuits. We
Yeah.
know exponential, I mean, as far as we know, for multilinear.
there's at least one paper where they're working hard to show a separation between multilinear formulas and multilinear circuits.
Right.
That might be
That's
what
the
you're
background.
thinking of.
But is it n to the log n really? I'm trying to now.
For determinant,
Yeah,
yeah.
yeah, back to,
Ron's
like from
first paper-
fuzzy,
the
but-
first paper on.
yeah, maybe.
Oh,
Okay.
It's on.
Yeah, but if that was IMM, Ran's thing was, if the determinant became the IMM, if your hard polynomial is the IMM, then yes, then it will prove lower bounds because of this reducibility.
So Ron's method, I mean, it's similar. I mean, it's just a part of this big matrix and
Yes. Yes.
it doesn't work. I mean, is there a reason why it doesn't work? I don't know, it's interesting. So you put a finger on what doesn't work there. I'm sure there's.
Also hell,
For formulas or for branching programs?
It's not IMM.
Right, okay, so it's the same.
It's the same
reason.
I mean, both, yeah. It's-
So why Ran's doesn't work for IMM already, right?
Yeah.
So the lower bound, the upper bound and the complexity of the polynomial is all the same, exactly the same, but. Yeah, for IMM, that's, I mean, we were also working on this, like, why is it, why is the IMM so stubborn? Like, what about it is, and I don't know that. So. I don't know that some measure of complexity does not work for the IMM, like. It could be some projection of the IMM. Maybe you take the IMM and you set some variables in it to 0 and you just play around with it and it can have higher the bounds work out just right. Like, a good question is to have some kind of barrier result in this setting also. Like, are these techniques just not strong enough to ever prove lower bounds for the IMN? And probably, but I don't know how to say that, look, this measure of complexity cannot work for the IMM. It's not just a matter of working hard and proving, doing a refined calculation.
To me, it's connected directly with the difficulty of connectivity. If you can find any algorithm for connectivity which has better depth than log squared circuit in any model, arithmetic, Boolean, we just don't know.
The reason you can use IMN is because the product, every slice has this rank 1 matrix. Right? It's a complete graph, and then when you multiply, then you get the same matrix, right? So is that like what if you have a different matrix in every layer?
The different 0-1 patterns. That's a great.
Yeah, you fix the matrix. What?
You have a different matrix in every layer.
The IMN is a complete graph.
Yeah, but they are different.
No, but the graph is the same.
The variables are different. What do you get? The
The graph
variables
is-
are disjoint.
The reason you can use this self-reducibility is that the complete graph times the complete graph is a complete graph.
No, it's because the variables are disjoint.
No, if you had a different graph,
Yeah.
a random graph here and a random graph here, the product would be a
I
different.
think that is what you're
That's
saying.
the variable,
I said the random
variables.
variable reduction, I meant there was, if you set some values to at random and you have expander graphs or something, maybe, like I don't know that it
No,
does
but
not.
it would be a project. I mean, you can set some of the variables to 0 and then you have a graph.
Right, but if you had a small circuit for some specific graph, it wouldn't give you a small circuit for many copies of the same graph. Okay, it's in the other direction.
I don't, yeah.
But I think I understand what Zev is saying, but I did think along that direction and I was not able to make it work, but I don't know that it does not work. Some clever projection of IMM doing something like that. Yes. For formula low bound. I don't know how to show that it doesn't work.
Question. All right, thanks.